Thank you, Leon. My name is Sebastien Mannai, and today I will present to you my research about acoustic fluid level detection for oil and water wells. I've been working on this with my advisor, Dr. Choon. So the question we're going to answer today is how much liquid, be it water or oil, is left in a well? What's the level of that liquid, and how can we determine this level? So two of the world's biggest industry care about this problem. The first one is the water industry. Water is a resource that is becoming more and more scarce. And in many areas, the water we drink or use for farming is pumped from aquifer resources. For example, 40% of California water comes from underground reserves. As water becomes scarce, you need to manage it with care and being able to know exactly how much is left on the ground. The second industry that obviously cares about what's on the ground is the oil and gas industry. There are millions of oil wells throughout this world. And in order to better manage an oil reservoir in an oil well, you need to know how much oil is left on the ground in real time. So how do people do that today? There's two big categories of technology. The first one is an underground sensor. You place a sensor at the bottom of your well, you connect it to the surface via a long cable or optical fiber. And this worked very well. However, the conditions at the bottom of the wells are extremely harsh, typically high temperature, corrosive environment, vibration, and so on. So that sensor is going to be very expensive and it's not going to last for a very long time. In addition, several miles of optical fibers are typically very fragile and it's a component that breaks easily. The second approach is you can determine that water level from the surface, which is a very good improvement. And the way people do that today is they bring an expensive piece of equipment connected to the well, create a shock wave that is effectively going to bounce down on the fluid level and reflect it back at the surface. And you time that wave very similar to an echo. That technology is proven. However, a technician typically carries the equipment from well to well. And so you're not able to observe the evolution of that liquid level over time. It's a one-off measurement. So why do we need to do this? The first reason is typically underground pumps are a very expensive piece of machinery. Here you have a diagram of an ESP pump for used by the oil and gas industry, which can cost around $500,000. And if the pump is pumping too fast, if you pump the well dry, the pump injects gas, and like most machines, it's designed to be lubricated. And with if it's pumping gas, it's going to fail extremely quickly. And here you see some broken impeller that result from this damage. So you could drastically reduce the failure rate of the pumping equipment and reduce the downtime of it. The second reason why you want to know the liquid level in the well is knowing the liquid level effectively gives you the pressure at the bottom of the well. And that pressure is directly correlated via various reservoir models to how much water or how much oil is left in that reservoir. So it is an extremely important metric. So the concept I'm going to present to you today is a blend of two ideas. The first one is if you've seen in movie or if you've tried as a kid or if you haven't, don't do it. If you put your ear on a rail, you can hear a train come from miles away, even before you see a train. And the reason is steel that the rail is built out of carries vibration extremely well with very little attenuation. The second concept is that the level of liquid in a container, in a pipe, affects the acoustics of that container. So if you blow in a bottle, the sound changes based on how much liquid is in that bottle. So the type of sensors I'm presenting today is a mix of those two concepts. The idea is that the pump located at the bottom of the well generates all kind of vibration that travels through the pipe that carries the liquid, the water or the oil to the surface. That pipe effectively is a string that's going to vibrate differently based on how much liquid level is around it. And the sound that is carried will change based on that level of liquid, which means the sensor at the surface will be able to determine in real time how much liquid is left in the well. So a lot of my work was on the modeling theoretical side. Various type of modes can propagate in a pipe. You can torsional mode, twisting of the pipe, flexural mode, which is what you have in a guitar string or shaking a rope, longitudinal mode, which is a compressing. So they can all coexist, some can propagate, some can't. And so a lot of modeling needs to be done to know what you will have to be listening to at the surface. So the next part will be to design a prototype. So a lot of the existing technology out there could be adapted for this prototype. For example, the picture here is a technician that is surveying a whale by using ultrasound technology. Um, so there's a lot of technology in the space that can be used and adapted to be able to measure the level of liquid in a well. And the second part will be to test this on a real world well. So the little diagram here is a wellhead, typically what you see at the surface of an oil well. And so you need to be able to package your sensor to fit into that component and to pass all the safety requirements. So I have been at MIT since my master's, working with my advisor, Dr. Choon. My master and PhD were with Siemens and Schlumberger, and I'm originally from France, where my background was in quantum physics and mechanical engineering. So thank you for your attention. I am looking for additional researchers or students to help me push this project further, as well as industrial partners to help us design a device and being able to test it in real world condition. Today, we are working on a patent, and tomorrow we'll be working on various experimental trials on the field. Thank you for your attention.